Welcome back! In April I unboxed the two Haswing Protruar 2.0 24V electric trolling motors. That's just the head here on the bench. During that video I noticed that the battery indicator was practically unusable. Card here, link in the description. Now, 6 weeks ago, we reverse engineered that battery indicator and came up with some ideas to make it somewhat usable. Another card here, another link in the description. Meanwhile, I've got the parts to implement those improvements. And that's what we'll do in this video. Enjoy! Just a short recap of what we're dealing with here. At the core, we have a quad comparator. Only 3 comparators are really used, and these comparators are driving the 3 LEDs of the battery indicator. One input of each comparator is connected to a 2.5 volt voltage reference. And the other inputs of the comparators are connected to voltage dividers that divide down the battery voltage at a critical voltage to those 2.5 volts from the reference. So if the voltage at the output of one of these voltage dividers goes beyond 2.5 volts, the related LED will light up. From the factory, the critical voltages of these voltage dividers are set to 22.6 volts, 21.5 volts, and 16.5 volts. So absolutely unusable with any kind of battery chemistry, be it lithium ion, be it lithium iron phosphate, or even lead acid. So I propose to exchange these resistors here to get critical voltages of 26.4 volts, that's equivalent to a 70% charged lithium iron phosphate, 26.0 volts, equivalent to a 40% charged lithium iron phosphate, and 24.0 volts, so 10% charge in a lithium iron phosphate. And now let's replace all these really tiny resistors. Okay, step 1 would be to get the old resistors off the board. Preferably without frying too much. Oh yeah, that's better. That was easy. That was even easier. And done. I hope my hand was not in the way too often and for too long. But yeah, step 1 is done. The next step would be to put here 3 0 ohm, that is bridges resistors on the board. Oh, looking good. Okay, next are the 3 resistors with different values, and now I have to be really careful. Next is R1 with 17.2K. Oh, looks good. Okay, then comes R2 with 31.2K. And now R6 with 17.4K. Yep. Okay. That one doesn't win a beauty contest, but as long as it's connected, I'm happy. And I almost forgot to solder the other sides. Looks nice enough. And now we flip the whole thing around. Okay, I have to remember that I only want to desolder the resistors, not the capacitors. I hope I can be precise enough. We'll see. Not quite up to temp, it seems. Oh, come on. Okay. And I removed the capacitor as well. Shite. I have the resistor here. But where did the capacitor go? Ah, I see it. Okay. Let's hope the next one goes a little bit better. Maybe I should up the temperature a little bit, which I'm doing right now. Okay, that went better. You just have to be patient and wait until the temperature is really up. Now let's see if I can reattach the capacitor. Looks good. Next we have R9 with 1.82K. Ooh, that is but ugly, but can't be helped. R8 with 3.32K. Ooh. And finally, R7 with 2K. Okay, that's really ugly, but it will serve the purpose. At least I hope so. Now, a big finger. Yeah, let's test that thing. Okay, let's test that thing. Yeah, we are already at 24 volts and the red LED is not on, but that's what our tolerance is for. So let's try 24.1. Oh, no. 0.2. No. 0.3. No. 4. Uh-oh. 5. Uh-oh. 6. Oh. I see a glimmer of hope. 24.7. Can I have you a little bit more of that glorious glow? Yeah. 24.7. Yeah, that's 0.7 volts off. That's not good. Okay, next LED should come on at 26 volts. So let's go to 26. And of course, it doesn't come on. 26.1? No. 0.2? No. 0.3? 4? 5? 6? I see a glimmer of hope. 7? Okay. It should... This is not good. This is not good. It's also... please note, that's also 0.7 volts off. So, and the next one should come on at 26.4. And if the pattern holds, I predict it will come on at 27.1. We are already above 26.4. So let's say 27.1. Interesting. So we have an offset of each and every LED of 0.7 volts. Question is why? Okay, let's probe that thing and see what is what. Just a reminder, the circuit diagram is so convoluted because I recreated the layout on the board. So here, we should have our reference voltage of 2.5 volts. 2.497. Good. And here I'm currently feeding in 24 volts. We should have 2.5 volts. If my voltage divider is correct and I... Oh, 2.433. Okay, 24 volts comes in here, goes into that resistor. 23.33. Okay. Let me probe somewhere else if I really get 24 volts into that thing. Come on. Yeah, 24.02. Curious and curious. So here we have 24.02. And yeah, this is a little bit small, but that's the positive lead coming in. And then I have my polyfuse. And at one end we have 24.02. And at the other end we have 23. That's a voltage drop of 0.7 volts. Which would explain why our values are all 0.7 volts off. But why do I have that voltage drop of 0.7 volts across a polyfuse? Let me switch all LEDs on. 1, 2, 3 LEDs are on. Now let's probe that again. And we are 28.4 volts. And we get in 28.4 volts. And on the other side we have 27.7. That's not a polyfuse. That's a diode. Excuse me. Let's zoom down on the board again. So that part is clearly marked M1, not D1, but yeah, it looks like a diode. MOD058, M0D058, or is that a B at the end? No, it's more like an 8. Let me look up that thing. Okay, it's a diode, and not the number is important, but that marking here, it's barely visible, but it's M1. And yeah, if you see on the left side the 2 stripes, it's a diode, but I will be verifying that. Okay, here is that little bugger. Let's try. Okay, diode 0.36, 0.37 volts. Okay, did I flip it? Sorry. Okay. Carefully. And isolating. So here's the new and improved circuit diagram, and the mystery part labeled on the PCB M1 is actually a protection diode against inverse polarity. The funny thing about that is that the Protruar manual clearly states that you shouldn't reverse the polarity because otherwise the motor will be destroyed. The reason being, while they have a reverse polarity protection for the battery indicator, I bet they don't have such a polarity protection for the motor itself, because even if they used a big Schottky diode, drop 0.3 volts or so, that's still at 40 amps, 12 watts that they would have to dissipate. So the only way to go would be, use some MOSFETs for reverse voltage protection in the motor electronics, and they are certainly too cheap for that. Anyway, you already saw the diode lying there, so I actually deleted it. Yeah, not a nice approach, but if you want to make precision voltage measurements, you cannot have a run-of-the-mill silicon diode here in between. And here's the high-tech stand-in for the diode. I soldered in. Sorry, something gave way here. Please note that 00 marking at that spot. So yeah, they somehow one part of the team intended to put there a 0 ohm resistor, and the other part of the team wanted a M1 diode, and don't ask me. So take 2 of the amazing improved battery indicator, now without reverse voltage protection. Okay, powering on, 23.9 volts. That's only half on. If I go to 24 volts, yeah, it comes on fully, and it goes off at 28.9. Very nice. Next diode should come on at 26 volts. So at 25 volts, we don't want to see anything. Okay, 25.5, we don't want to see anything. 25.9. It's coming on a little bit, and 26. Woo! Yeah, spot on. And the last one should come on at 26.4. So 0.1, nothing. 0.2, nothing. 0.3, nothing. 0.4. Ah, there it is. Ah, okay. That was quite a journey. That's it for today. Yeah, I expected that to go a little bit more smoothly, but it shows if you do some reverse engineering, and at least with Chinese PCBs, don't rely on the markings on the PCB. Still my fault. Anyway, we have now a relatively usable battery indicator for lithium iron phosphate 24-volt nominal batteries on our outboard. Great. Next week, we will continue with the... Yeah, not a good day today, but anyway, full fly-by-wire electric outboard project. Till then, bye.